For this lab, I observed the motion of a falling object. I dropped a baseball from a height of about 1.3 meters. It reached the ground in about half a second. I used the program Tracker to track the actual location of the ball in the video and the programming language VPython to create a computational model. During this time, the ball was acted on by two forces, gravity in the negative y direction and drag in the positive y direction. Starting from Newton's second law of F net equals ma, we first assume that F net equals the force due to gravity minus the force due to drag. For the moment, we are going to ignore drag. In this situation, the force of gravity on the ball is equal to the gravitational constant negative 9.8 meters per second squared times the mass of the ball, 0.149 kilograms. We are able to cancel out mass on both sides of Newton's second law to get that acceleration is equal to the gravitational constant. We can then plug it into the equation final velocity equals initial velocity plus acceleration times delta t, where acceleration is the gravitational constant. We can also use the equation final position equals initial position plus final velocity times delta t in order to approximate the position of the ball. Here is the computational model with gravity as the only force acting on the ball. I used a delta t of 0.033 seconds because the computational model was originally underpredicting the position of my ball. I will explain why this overestimation was necessary in a minute. Here is a graph of the position of my ball based on my data from Tracker, as well as the data from the computational model. As you can see, the line begins to overestimate the distance the ball has traveled as time goes on. This overestimation occurs because I did not include the drag force in the model. When the ball falls through the air pushes against the ball in the opposite direction of its motion. There are several types of drags. For this situation, we use turbulent drag. Turbulent drag is caused by chaotic changes in a fluid, in this case, air. The equation for turbulent drag is negative b, which is a constant, times the velocity squared. Here is the computational model with drag included. As you can see, the blue arrow, drag, points in the opposite direction of the motion of the ball, as well as gravity, the yellow arrow. Here is the graph of the computational model with drag compared to the Tracker data. As you can see, it matches the Tracker data better than the graph without drag. Granted, there are still some points where the Tracker data does not line up perfectly. This is because the camera had some bad shots of the baseball and I had to guess where the ball was. Here are the graphs of the two models combined. You can definitely see here that for the most part, the model that has drag better approximates the Tracker position than the model that does not have drag. When an object falls for a long enough time, it can experience what is called terminal velocity. Terminal velocity occurs when the force due to drag is equal to the force due to gravity. When this happens, the object does not experience any acceleration and has a constant velocity. Because the ball only fell for half a second, it did not have enough time to reach terminal velocity. However, if I let the computational model run for 5 seconds, the ball reaches a terminal velocity of negative 6.976 meters per second at 2.5 seconds. If I were to throw the ball downwards, the terminal velocity would still be the same. The only difference is the amount of time it would take for the ball to reach terminal velocity. This is because drag is dependent on velocity. As long as the gravitational force remains the same, the terminal velocity will remain the same. I demonstrated this in another computational model. This time, I gave the ball a negative 5 meters per second velocity in the y direction. Again, the ball reached a velocity of negative 6.796 meters per second, but this time reached that velocity at about 1.5 seconds. As we can see from the graphs, the ball will either continue to accelerate unless the ground stops the ball, or it reaches terminal velocity due to drag.